Hello, hello. Am I audible?
Yes, sir.
Okay, just 1 minute.
রেকর্ডিংটা অন করে দিয়েছেন তো?
হ্যাঁ। So that was last discussion. So how to classify group of order, right? Okay. So if there is elements of all elements of order 8, there is a element of order 8, then it is cyclic. Then if there is no element of order 8, then order must be 2 or 4. If there is element of order 4, then what, and all element of order 2, then it is abelian. All we have uh, proved here. Okay, so all non-abelian group we have proved this way, that if the element of order 8, then it is cyclic. So uh, each element has order either 2 or 4. If all element have order 2, then it is abelian. So there exists an element of order 4 such that it is 4. So G mod is isomorphic to Z mod 2Z because it is order 2 cyclic, and we have shown that it is either D8 or quaternion. Okay. Now then uh, I was asking that uh, order groups of order 12. To do it systematically, we have to understand some product in group theory. So I'll just do it some briefly, not elaborately. Okay. First I add pages 12. How to draw? Okay. Some definition. Let K be a subgroup then a subgroup Q is a complement of K in G equals to identity and KQ equals to G. Recall that KQ is a subgroup of G if and only if KQ equals to QK. Okay. Note that a subgroup K of a group G need not have complement for example take G equals to S3 and K equals to A3. No, need not have complement. No, এখানে কমপ্লিমেন্টটা হয়ে যাবে even if it exists then they even if it is exists then it may not be unique. K equals to A3 if Q is any two cycle group of এখানে A3 টা নরমাল এখানে কমপ্লিমেন্টটা পেয়ে যাবে এর cyclic subgroup of order 3 order 2 that is generated by 1 2 or 2 3 or 1 3 then Q intersection A3 is identity because A3 it is 3 cycle identity of S3 now A3 is normal so and A3Q equals to G. Okay, because A3 normal so A3Q is a subgroup. You know that if one of them is normal K or Q then KQ equals to QK, hence KQ is a subgroup. So A3Q is a subgroup and you can use the what is order of HK order of h into order of k divided by order of h intersection k. Using this formula, it is order of 6, so it is actually G S3. Okay, actually S3. So, but it is in this example it is not unique. Okay. Now, can you find an example where complement need not exist? You have to take not normal subgroup, non-normal subgroup. Okay, think it. Definition: a group G is a semi Q if K is normal in G and K has a complement that isomorphic to Q. Okay, that isomorphic to Q. Some lemma: if K normal subgroup of G, the following are equivalent. This is very important, this discussions. Number 1, G is semi-direct product of K. Number 2, there is a subgroup Q so that every element has unique expression AX. There exists a homomorphism S G with canonical projection. Natural map. There exists a homomorphism with K X for all image theta. So these are all equivalent statement, and very important this proof. One implies two. Suppose G has a complement Q in G with isomorphic to Q. Because see that definition, K has a complement Q1 with Q. Okay, complement Q1 with Q. Q1 is a subgroup of that G. Okay, now I have to show that this expression is unique. Okay, for every element we have K intersection Q equals to identity and KQ equals to G. So G belongs to G implies G belongs to KQ. This implies G equals to AX for some belongs to K and Q. If G equals to, so it has expression AX equals to BY. B belongs to K, Y belongs to Q. Then what happened? So this implies B inverse A equals to B inverse A equals to Y X inverse, and that belongs to K and that belongs to Q. So this implies B inverse A, and they are equal, belongs to K intersection Q. This imply A equals to B. Yx inverse belongs to K intersection Q. Yx inverse belongs to K intersection Q. This imply, and this is identity, right? X equals to Y. So every has a unique expression. This 2 implies 3. So you have every G has unique expression. So there is a morphism G to K. So you have a morphism that identity to K to G. This is inclusion and this is projection G mod K. Again, so I write here. I'll stop. Now you have to take another homomorphism S. You have to construct S. What is S? How to define it? So define so you know that K G goes to Kg goes to X. How to what is G? Where G equals to Ax unique expression, where G equals to G equals to unique expression with your X belongs to A belongs to where your K, and X belongs to your Q, that is isomorphic to G mod K. Okay, X belongs to Q. Okay, now is it well defined? Is it well defined? Let Kg equals to K G1, that is G2. That means what? That means two left coset are equal when G1 G2 inverse belongs to K. Now G1 equals to A1 X1 and G2 equals to, let G2 equals to A2 X2. So G1 G2 inverse is A1 X1, sorry, X2. I should write X2. A2 X2 inverse, that is what? That is your A1 x1 x2 inverse a2 inverse, right? Let so what I can write it as a1 x1 a1 inverse, then a1, okay, x2 inverse a2 inverse. I should write a1, so this belongs to k. I can write it as a1 x2 inverse a1. No, I should write here. So a1 belongs to k, right? Sorry. So you have to show that x1 equals to x2, x1 equals to x2. What is happening here? So I want to define a homomorphism G mod K to G and want to show that it is well defined. So one way is your, if G2 G G2 G G mod K to G, when this morphism exists, if kernel is contained in K. Okay, so how to write it is, see, G K G, that is K A X. Now A belongs to K, that is your Kx, because A X X inverse, it is your A belongs to K. So Kg1 equals to Kg2, so I can write it as and G1 equals to A1 x1, G2 equals to A2 x2. So I can write it as K, this is equals to Kx1, this is equals to Kx2. This is the reason Kg equals to Kx. Now I have to note that two coset are equal, so x1 x2 inverse belongs to K. Now x1 x2 belongs to Q. This implies x1 x2 inverse belongs to Q also. So x1 x2 inverse belongs to K intersection Q, that is your identity. This implies x1 equals to x2. So it is well defined. This implies S is well defined. So G1 K G1 G2 S K G1 K G2 is K S of K x1 K G1 G2 K x1 into K x2 equals to S of K x1 x2 equals to x1 x2 that is definition of your S. So that is your S kx1 S kx2 S kg1 because they are same S kg2. That is note. Okay, so it is a homomorphism. S is a group homomorphism. Next, you have to show that pi compose S is identity. Pi S kg1 pi S kx1 equals to pi x1 equals to kx1 equals to kg1. So it is identity. Again, pi compose S equals to identity G1. Okay, check that Q to G mod K x1 goes to kx1 gives and isomorphism. That means theta restricts what is S restricted to Q gives an isomorphism. Oh, not that is not X restricted to Q. I should write pi restricted to Q. Pi restricted to Q, that gives an isomorphism. Okay, now so last one is there exists a 3 implies 4 there exists theta G to G with kernel theta K pi x equals to. So what is your G to G homomorphism? What is the G to G? You have pi G to G mod K and G mod K to GS. So G to G, take theta equals to S compose pi. Then what is kernel theta? You have to show that kernel theta equals to K and pi x equals to x for all x belongs to image theta. Let x belongs to K. This implies Kx equals to K identity. Now S compose pi of x equals to what? S k x equals to S k identity equals to identity. So k is subset of kernel theta x equals to that theta. Conversely, x belongs to kernel theta implies S compose pi x equals to identity, sorry, I should write identity G, that is S of kx equals to identity, that means x equals to identity. Okay, so k equals to kernel theta, and you have to show last one is pi x equals to x for all, sorry, I should write theta x equals to x, that is not pi x, I should write theta x. I should write theta x equals to x, because pi is projection, theta x equals to x for all x belongs to ms theta. So if y belongs to image theta, so y equals to s compose pi of x for some now theta y equals to s compose pi compose s compose pi, I write here of x. Now by 3 pi compose s is identity, so s compose identity compose pi of x, that means s compose pi of x, that is theta y, sorry, that is y, done, and we are done. Now 4 implies 1, so you have a map theta to theta g to g with, we have kernel theta k and theta square is identity, right? That means theta x theta square is identity. So we need to show that k has a complement G has not. K has a complement. K has a complement. We need to show that what is the problem. K has a complement in G. Okay, we need to show that. Now kernel theta, it is normal as kernel theta is K, so K is normal. So you have to find a complement, right? Let Q equals to image theta. Claim K intersection Q is identity. Okay, K intersection Q is identity. If X belongs to K intersection Q, that is X equals to theta Y for some Y belongs to G, because it is lies in image, Q is image. So theta X equals to theta square Y equals to Y, because theta X equals to X, that is theta Y, I write. Theta square Y, that is identity, because K, that is your theta Y as, but it is identity as theta X equals to X. I write theta not X, I write theta T. It is very disturbing. T equals to T for all T belongs to image theta. So that is identity and that is your X. So X is identity. So it has a complement. Done. So we have done a very important lemma. Example. Example. Sn is a semi-direct product of a n by z2. Obviously, it is obvious. Normal in your Sn. Now Sn, so can you find a homomorphism from here to here with it is identity, or by definition what happened, or it has unique expression? Any four of it. Can you find? take Q is identity and 1 to cycle. So I am claim that uh, obviously an intersection Q is identity because 1 2 is odd cycle, as 1 2 is odd. This implies 1 2 does not belongs to an. So Q is a complement and an Q is an normal, so an Q is a subgroup. An Q cardinality is your n factorial equals to cardinality of Sn. So this implies an Q is, I am using the formula a cardinality of Hk is cardinality of H into cardinality of K by cardinality of H intersection K. N Q is your Sn. Q is a complement of An in Sn. This implies Sn can be written as An Q. Okay. Now this is isomorphic to Z mod 2Z. So I can write as 2Z. Okay. Homework. D2N is isomorphic to Zn symmetric product Z. Zn means Z mod Nz. Z mod Nz symmetric product Z mod twice Z. Okay. Now there is very important lemma. Let G is symmetric product of K by Q. Then there is a homomorphism theta Q to odd K, automorphism of K, defined by x goes to I write x goes to theta x. What is theta x? Theta x K to K, where A goes to x inverse conjugation. Moreover, for all x, y and identity Q to K, That means theta is, I want to write, it is homomorphism. It is obvious because K is normal. Okay. It is obvious because K is normal. K normal in G because it is given. This implies theta x belongs to odd kx. Uh, why it is automorphism? You know that it is restriction of gamma is inner automorphism, G to G, it is restriction and it lies in K also. Now why theta is surjective? Why theta x is surjective? Theta x of A belongs to K for all A belongs to K. So okay, and theta is injective. Theta x A equals to theta x B, that implies x A x inverse equals to x B x inverse. This implies A equals to B. This implies theta x is injective. Now let T belongs to K, then theta x x inverse T x is your x inverse T x inverse, that is T. So theta x belongs to odd K. So rest theta x y equals to theta x y, just put it and check it. Rest are checking. Okay. Definition. Let I write this. Let G equals to, that means K is normal, and theta Q to odd K be a homomorphism. I should write this way. Semi-direct product, let K normal in G and Q subgroup of G and theta homomorphs. Now this theta real, hello, realize the a semi-direct product K just 1 minute, just 1 minute. Okay, a semi-direct product G of K realize theta if for all x belongs to Q and A belongs to K x inverse. Okay, given groups Q and K and a homomorphism theta Q2 odd K define দুটো আরবিট গ্রুপ থেকে একটা নতুন গ্রুপ তৈরি করছি we are constructing a new group using this theta. Okay, set, what is set? Just Cartesian product but operation are different. Set is Cartesian product but operations are different. Operation with check that group theorem is a semi-direct product of K by Q that realize theta. This is last theorem about this semi-direct product. Okay, and converse part also true. That was last theorem. Okay, so what you need to show here, number one, we need to show, we have to prove that we have to prove that number 1, K is normal subgroup of G. Number 2, Q is a subgroup of G. Number 3, what is K? K means K, that is Q. K means K comma identity, that is we identify with K. That is Q. So where K is identified with K is identified with K cross EQ, where Q is identified Q K intersection Q identity KQ is G, that means K, now theta is that realized theta, okay, that realized theta, the symmetric product realized theta. That means x goes to theta x of A equals to, that means A means here A comma identity, so equals to I should write better way, theta identity K comma x of A comma Q is x A x inverse, that means x inverse. So with respect to this operation you have to check this, okay. Converse part of this theorem, proof is homework, next day I will discuss it. Converse part is if G is a symmetric product of K and Q, then there exists theta Q toward K with G isomorphic to Q. Okay. This proof is very easy. Define theta xa is x inverse so this type. So now what is the importance of this class? This is your systematic way of classification. You have to find a normal subgroup, then you have to find a complement Q, and you have to find all homomorphism Q to odd K is normal. Then each homomorphism will define a new group, that is this group K semi-directed theta Q, and this is your classification. So you have to find a normal subgroup K, then you have to find then quotient it out G mod K. Suppose G mod K is your G mod K isomorphic to some group, I don't know, it may be Dn, it may be Zn, that is what. So you have to find all homomorphism from G mod K to odd K. Each homomorphism will define a group via theta. And what is the multiplication? Multiplication ax by is a theta xb comma xy. So this is your systematic way. So now if I ask you find or classify all groups of order 12, classify all groups of order use 16, this type of groups. You can do it for any group, even order 8, order 8 and order 4 abelian group. It is easy because semi-direct product is exactly your direct product, but if it is not abelian, then it becomes difficult. Okay, so groups of order 12, groups of order 16, 18, So what is the systematic procedure? So find a normal subgroup K, quotient G, find G quotient K. That means easy isomorphic copy. G quotient K isomorphic to Z, SN, yeah, DN, whatever standard groups. Find G quotient K. Then find all homomorphism from G quotient K to that odd K. Each homomorphism will define a group. That is your classification. Okay. If you have any question, please ask me. I will discuss it. Discuss classification next day. কোনো কোশ্চেন থাকলে বলো। বলো কোনো কোশ্চেন থাকলে বলো। ধরো গ্রুপ অফ অর্ডার 8 আমরা আগের দিন যেটা করলাম, সেটাকে যদি আমি এই সেমি ডিরেক্ট প্রোডাক্টদের দেখতে চাই, যদি অ্যাবেলিয়ান হয় তাহলে ওই সেমি ডিরেক্ট প্রোডাক্ট আর চেক দ্যাট অ্যাবেলিয়ান হলে সেমি ডিরেক্ট প্রোডাক্টগুলো ডিরেক্ট প্রোডাক্টের সাথে সমান হয়ে যাবে নর্মাল যদি থাকে। আচ্ছা, নন অ্যাবেলিয়ানের ক্ষেত্রে প্রবলেম। তাহলে আমি দেখেছি যে একটা অর্ডার যদি 8 অর্ডারের হয় তাহলে তোমার এলিমেন্ট থাকলে অ্যাবেলিয়ান হবে, অল এলিমেন্টের অর্ডার যদি 2 হয় সেটাও অ্যাবেলিয়ান হবে। তাহলে একটা 4 অর্ডারের গ্রুপ আছে, 4 অর্ডারের এলিমেন্ট আছে, 4 অর্ডারের এলিমেন্ট দিয়ে জেনারেটেড গ্রুপটাকে সাইক্লিক হবে, কি যে Z4 হবে হোয়াট এভার। কে হলো একটা এলিমেন্ট অর্ডার 4, তাহলে ওটা Z4 হবে, সরি অর্ডার 4 দিয়ে জেনারেটেড গ্রুপটা নিয়ে নাও Z4। তাহলে অটোমরফিজম অফ Z4 কত হবে সেটা বলো, কত হবে? আচ্ছা, এবার জি মড Z4 কত হচ্ছে, সেটা হচ্ছে Z2। তাহলে Z2 থেকে অটোমরফিজম অফ Z4 এ কতগুলো হোমোমরফিজম পাবে, প্রত্যেকটা থিটা একটা করে গ্রুপ ডিফাইন করবে। বলো অটোমরফিজম অফ Z4 কত হবে, অট Z4। তার মানে এখানে বুঝতে পারছো অট গ্রুপটা ক্যালকুলেট করাটা খুব ইম্পর্টেন্ট। ওকে, ঠিক আছে।